Hello everybody and welcome to another episode of Science with Mr. Emond. Today we are going to be starting our second unit on heat. We're going to be focusing on enthalpy in this unit. Let's get started. So first we're going to have to go over some of the new terms that we're going to be talking about today. The first term is enthalpy, which is what the unit's about. And enthalpy is the total amount of thermal energy in a substance. Okay, so it's the total amount of thermal energy in a substance. The enthalpy change, therefore, is the amount of energy released to or absorbed from the surroundings during a physical or chemical change. So whenever you do a chemical reaction, there's going to be a movement of energy, and that's going to be the enthalpy change, delta H. Now, the energy change, it can be measured using calorimetric data, like we just finished learning about in HT1. And so calorimetric data tells us about the heat content of a system, which is annotated using the symbol Q. Now, Q can be positive, right? If Q is positive, then the heat is being gained by the system, and if Q is negative, it's being lost by the system. Delta H of the system, or the change in enthalpy in the system, is therefore equal to the absolute value of the heat content of that system. So we don't care about whether it's plus or minus, we're always going to treat it as plus. For a chemical reaction, the change in enthalpy is given by this equation. The change in enthalpy is going to be equal to the enthalpy content of your products minus the enthalpy content of your reactants. And you can kind of think about it in terms of this. The differences in the energy contents of the bonds of your products and your reactants, that's going to be the change in enthalpy. Okay, let's talk about exothermic reactions. So an exothermic reaction is something that we would have talked about in Science 10, and an exothermic reaction is something that we know releases heat. So our general definition is a chemical reaction that releases thermal energy to its surroundings. That's an exothermic reaction. And this we're going to have to tie into the law of conservation of energy, because we just learned earlier that the law of conservation states that energy cannot be created or destroyed. It just moves from one place to another. And so the total energy between a chemical system and its surroundings must be constant, both before and after a chemical reaction occurs. So it doesn't just disappear. And now we talked about energy being in the bonds, right? So one thing I want you to think about when it comes to exothermic reactions is if more energy is released from the formation of new bonds, these are in your products, right? If more energy is released in the formation of those new bonds, then is required to break the bonds in their reactants. So remember, in order to make our products, we started off with our reactants, and we have to break those compounds apart, shuffle them around, and put them together in different ways to make our new products. So if the amount of energy released, I'm going to take out my little pencil here. If the amount of energy released in my products is greater than the amount of energy released in my reactants, so this is a large quantity of energy, this is a smaller quantity of energy, then the chemical reaction is going to release energy to its surroundings. Energy is produced in the reaction. Okay, think of it as like a balancing scale with more energy being released on the product side, and that energy, of course, is going to go to the surroundings. So this is going to kind of give you some starting points for thinking about exothermic reactions. When you're looking at a reaction, if you see energy on the right-hand side, it's an exothermic reaction. This energy is going to the surroundings. It's being released. And so we have an example of that here. If you have two molecules of hydrogen gas and two molecules of oxygen gas, those bonds are going to have to be broken. right? So then you're going to have one single H, well, actually 4 single H's and 2 single oxygens that are going to get reformed, reshuffled into the product H2O, and there will be 2 moles of that, okay? Well, when that happens, more energy is released from the forming of these new bonds than is actually released or required to break these bonds. So therefore, in this reaction, 572 kilojoules of energy is going to be in excess and released on our product side to the surroundings. So the energy we can see here is on the right side of the equation. It's exothermic. Now, usually or sometimes, energy is not actually going to be in the equation, like here. It's just going to be what's actually mixing, right? So our hydrogen gas and oxygen gas mixing to form liquid water. Sometimes delta H is written off to the side like this. Delta H is equal to negative 572 kilojoules. Notice that the energy is the same. It's 572 kilojoules. What's different? Well, this is a positive value and this is a negative value, right? One thing to note is when energy is in a chemical equation, it's always going to be positive, okay? Because this is saying that energy is being released on this side, right? Even if it was on this side, you'll see in a second, the energy would still be positive, meaning that the energy is required to break the bonds. On this side, it's saying the energy is being released. So no matter what in the equation, it's positive. However, when it's written off to the side, if delta H for the system is negative, the reaction is exothermic. We know that it is exothermic because it's on the right-hand side of the problem. And so our delta H, of course, will be negative. Our delta H is going to be a negative value. Let's go ahead and try out a couple problems. Before we do that, actually, let's talk about endothermic. I think we're going to kind of fly through this because it's basically the opposite, right? So an endothermic reaction, you're not releasing energy, you're actually absorbing thermal energy from the surroundings. So you're pulling heat in from the surroundings into the system, okay? And we can kind of think about this in the reverse terms, right? If less energy is required, or if less energy is released from the formation of new bonds, okay? So when we're forming new bonds, of course, energy is going to be released when you form those bonds, but only a small amount. If less energy is released from the formation of those new bonds, of course, in the products, then is actually required to break the bonds in the reactants. So the amount of energy required in the reactants in order to break these bonds is actually quite high. Well, then where's your balance? It's on the reactant side, right? When this happens, then that energy is going to have to come from somewhere. And where is it going to have to come from? From the surroundings. So the system is going to have to absorb energy from the surroundings. And this is what's going to make it endothermic, right? So where is the energy here? It's on the left-hand side. So whenever you see energy on the left, it's endothermic. When you see it on the right, it's exothermic. And so you can see in our example here, there's energy. It's on the left-hand side of our equation. So therefore, this one, when you mix liquid water and break it down, it's going to form hydrogen gas and oxygen gas. This is endothermic, okay? More energy is required to break these bonds than it is to create these new bonds. Likewise, when you do not have energy in the actual equation and it's off to the side, you guessed it, it's going to be positive this time. Why positive? Because that heat's going to have to be gained by the system. We need the energy to break the bonds. So we're going to be pulling energy from the surroundings into the system, and therefore the heat content of the system is going to increase. So if delta H is greater than 0, the reaction is going to be endothermic. So a positive delta H, endothermic, energy on the left, endothermic. Let's go back here. Negative delta H means the system lost energy. The energy went to the surroundings. It's no longer in the system. So it's a negative value. If delta H is negative, that's exothermic. If energy is on the right-hand side, that's exothermic. Okay, if you need a little bit more of an explanation on how this all works, what's the difference between endo and exothermic, there's another video here which we'll watch on the live stream together. But for those of you on YouTube, just go ahead and click this link up here and you'll be able to take a break from my video, watch this one, review it, and when you're done, come back. If you don't need to watch it, we'll just continue on right now. For those of you who watched that video, welcome back. Let's go ahead and try out a couple questions here. Are these exothermic or are they endothermic? Go ahead and pause the video now and try these out for yourself. Welcome back. All right, let's go through these real quick. So in question A, here's my arrow. Where's the energy? It's on the right-hand side. Well, if energy is on the right-hand side, it is exothermic. So this one is exothermic. Let's do B. This is on this is the arrow. There's no energy within this. Instead, it's over here as a delta H. Delta H is negative. If delta H is negative, what does that mean? That means that my system lost energy. Where did the energy go? To the surroundings. Well, if the energy was released to the surroundings, that would make this exothermic. Good. Let's look at C. Here's my arrow. Energy is on the left-hand side. That makes this endothermic. The energy is required to break these bonds to form our products. So this is an endothermic reaction. Let's do D. No energy is within our chemical equation here. It's off to the right this time. This is a positive value. Positive value means the heat content, the change in enthalpy of our system is going to increase, which means energy flowed into our system. There was an increase in energy in our system, which means we absorbed energy. Absorbing energy is endothermic. There we go. All right, that's going to be it for this video. Stay tuned for our next video where we're going to go over Hess's law. See you soon. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.